Hello. Okay, so today we're going to talk about graphs. So I love graphs, so I'm going to give you a big old woohoo for that. Okay, ready? Woohoo! All right. Okay. Good. Okay, we're going to talk about Euler a couple of times. We're going to tell you what graphs are and what they can model. We're going to tell you a cool fact. We're going to tell you about Euler again, and planar graphs, and Euler again, and then and so on. We like Euler today. Okay, so let's look at this problem. Okay, so here's this city. I guess it's Königsberg. See, there's these bridges here over these rivers, right? There's an island in the middle. There's a couple of. There's this south side and the north side. This island in the middle. I don't know what the in between side, right over here, right? So what Euler started with was that can you have these are quite beautiful. Apparently, it's a nice city. Apparently, and apparently the bridges are where people go for strolls at night, and with their loved ones, or not, and then or by themselves if they're lonely. So the question is, can you go start at your house? Maybe you live on the South Shore. And go and take a walk and visit every bridge once. Cross all the bridges once, right? Because once you've seen it, it's a little bit annoying to go over it again. Okay? So that's the question. So what we're going to do is we're going to model this with a graph. We're going to, instead of north side, south side, we're going to sort of abstract away all the details we don't care about. That's what a model is. So we'll just say, for this problem, let's make this thing, we'll call it a vertex, A, for each body of land. Okay? And now what we're going to say is, what the bridges are ways to get between these bodies of land, so we'll connect, that'll correspond to the bridge on the left, that will correspond to the bridge on the right, those two correspond to the bridges between the island and the south part. There's the connections. Each one of those edges corresponds to a bridge. Okay, so now the question is, can you draw a tour in this graph? Now we're throwing away, in some sense, all this other information we don't need, and just writing down what we need to address the problem. Okay, so this is the problem in this object, which we're calling a graph. I'll define it more formally in a minute, and. Do you think you could, so I'm throwing away everything else, and I'm saying, can you draw a tour in the graph where, I'll call those things edges, I'll again define them formally in a minute, and or more formally, and can you draw a tour in this graph so you visit each one, you cross each edge exactly once? So, who thinks yes? Okay, who thinks no? Wow, you guys have seen this before. Okay, or you're just really Berkeley students, so that's fine. Okay, so great. Okay, we'll see. Okay, so did somebody have a quick argument why you can't do it? Anybody want to hazard a guess? A lot of hands went up. Some of you must have a reason. Yeah, okay. Right. Right. He says it's odd. This vertex over here, for example, D has odd degree, and that makes it. If you visit something and you visit again, these visits sort of pair up when you enter and leave, and so you can't possibly. Or the parity is wrong. Okay. So, and that's actually correct. It says that you can't do this because. The parity is wrong for these. There's some odd degree vertex. Actually, there's a lot of odd degree vertices, right? Okay? And in fact, it's kind of funny. There's an even number of odd degree vertices. Interesting. Okay. So here's that graph again. So more formally, G equals is two sets, V and E, where V is a set of vertices and A is a subset of the pairs of vertices. Okay. A and B is an edge in this particular graph. A and B, A, B, C, and D are the vertices, and these are the edges. Okay. So you'll notice in this particular graph there's two edges between A and B. So you would have to, sort of add information to say these are different somehow, because they're not identified only by the endpoints. Usually in 70 we're going to talk about simple graphs. If we don't specify and it's undirected, we think of it as a simple graph. Okay, meaning there's only one edge between any pair of vertices. Okay? Simple means you would not have no parallel edges. So this is a simple version of this, right? Okay? So a simple graph just doesn't allow these two edges between A and B. So, which we call parallel edges. Okay, so that would be called the multigraph. If you ever have a question, just ask. Okay, so the directed graphs, you could also have directed graphs. E equals VE is a set of vertices. E is a set of ordered pairs. I changed the base set into integers or natural numbers instead of letters. It doesn't matter how you specify what the vertices are. And here are the edges. Now these are directed. This time they're ordered pairs, right? From 1 to 2 means an edge from 1 to 2. And from 1 to 3 means an edge from 1 to 3. Okay? Okay, so this could be a model for, we saw already that undirected graphs are a model for something. These are a model for maybe one-way streets and you want to get somewhere. A tournament, we saw a tournament was a notion of somebody beats somebody. Precedence, one has to be before two and so on, right? Like this could be like I better put on, 1 could be my underwear and 3 and 4 could be my shirt and pants. So I have to put on my underwear first, generally. That mistake is embarrassing to do it the other way. So there's a social network. What's a social network? Is it directed or not directed? It could be either, right? You could have friends and they're generally undirected. You could have likes. They could be directed, right? I could like somebody and they could not like me. Sometimes in happy circumstances, it's both ways. People like each other, which is good, right? So in directed graphs, we will sort of in general allow these. These are not parallel edges, right? They go in different directions, right? 1 goes to 2 and 2 goes to 1. So in directed, these are not the same edge. They really have different meanings. Okay? So these are the concepts and definitions. And so we have... these are terms: neighbors, adjacent, degree, incident, in degree, and out degree. Okay, these are all sort of the natural definitions. Okay, but let me just show you. What are the neighbors of 10? Yeah, it's 1, right? Is somebody connected by an edge, right? It's a natural thing. 5, 7, 8, right? Everybody understands what the neighbor of a vertex is. You take all the edges whose endpoint with an endpoint that's 10, and you look at the other endpoints. Okay, does that make sense? The neighbor is an absolutely natural thing. So U is a neighbor of V if the edge UV is an E formally, but it's what you think, right? Okay, so edge 10, 5. Now I'm going to talk about an edge. Now an edge can be incident to a node. Now, I'm setting up these definitions to make some arguments nice. So this time, pay a little attention to this definition, okay? So 10.5 is an edge. That's an edge. That's the object I'm talking about. I'm talking about that little line, the representation, that little line between 10 and 5 is supposed to have turned blue, but it did not. Okay, and it's being willful. 10 to 5. Okay, so I would say that little line between 10 and 5 is the edge that's incident to vertex 10. It's also incident to vertex 5. So how many vertices is an edge incident to? 2. right, in a simple graph if you don't have loops. Okay? Okay, degree of vertex 1. Here again, it's sort of the natural definition. Everybody knows. What's the degree of vertex 1? It's just the number of neighbors in a simple graph, right? Or the number of another way to define it, you could sort of define it as the number of neighbors in the edges, or the number of neighbors of vertex 1, or you could define it as the number of incident edges. Okay, so I'm using the definition, so some proof in a minute is going to go really smoothly. Okay? Okay. So it equals the number of neighbors in a simple graph. I mean, if you have parallel edges, then you can define all these things as well. So now for a directed graph, you can define all the standard things, but let me just define a couple of them. Is in degree, what's the in degree of 10? 1. Okay, what's the out degree of 10? I think it's 3, right? There's 3 arcs leaving 10. Okay? Okay, so those are the basic definitions, right? I think we defined them all here. Okay? Questions on this? Okay. Okay, the sum of the vertex degrees is equal to the total number of vertices. Okay, so now you have practice with the definitions. So the total number of vertices is the sum of the vertex degrees is what I'm asking about. Okay? The total number of edges? Yeah, maybe that's a better answer. I don't know. What? Okay, which one? What do you think? I don't know. Any guesses? Who thinks A? Who thinks B? Okay, B is closer, okay, but not A is a triangle. And it's also not B, okay, because, here it's a triangle. And I think now it's like, what? Okay, what? Okay, what? Okay, what? For triangle, the number of edges is 3, and the sum of the degrees is 6. And the number of vertices is also 3, and the sum of the degrees is 6, right? Every vertex has degree 2. So 2 plus 2 plus 2 is 6, right? So therefore, what do you think the right expression is? 2 times E or T times V? That works for the triangle. Right? Either one of those things are perfectly good theories that the triangle doesn't falsify, right? But now let's look at this concept of incidences. How many incidences does each edge contribute to? How many? If you start counting about all the edge vertex incidences, each edge is incident to 2 vertices. So how many edges how many incidences are there total between edges and vertices? 2 times the number of edges, right? 2 times the number of edges incidences are there in total, right? Okay? So now let's count these incidences in a different way. Right? Remember, there's an edge and a vertex involved in the incidences, right? And now we counted it from the edge point of view. The edge says, oh, I'm involved in 2 of these interactions. I'm counting these interactions between edges and vertices that I called incidences. Well, the vertices can also count them. They could say, how many incidences am I involved in? How many is that? For a vertex. Its degree, right? The degree of a vertex is the number of incidences, edge incidences. So what is the degree of V? It's the incidences contributed by V. It should be by V. Okay? Right? An incidence involves 2 things, an edge and a vertex. So you could count it from the point of view of the edges, and you can count it from the point of view of the vertices. And for the vertices, it's the sum of the degrees. Okay, so now we counted the same thing twice, and we got 2 different expressions. We counted the number of incidences between edges and vertices from the point of view of edges, and we got 2 times E, the size of E. What we also counted the incidences, the total incidences from the point of view of vertices, and we said that's the sum of the degree. So what must these 2 be if we're counting the same thing? They have to be the same. So these 2 expressions are the same. Okay? The sum of vertex degrees, or digresses, or degrees, is also 2 times v. Okay, size of v. Okay, cool argument, right? Very nice. Right? Very nice. Yeah, we're going to cover a lot today, but that was so, that's one of the arguments you should really understand. Okay? Okay, now a path in a graph is a sequence of edges. Okay? So now, is this a path? That's sort of a sequence of edges. Would you call that a path? Is that what your intuition is for a path? No. The path is what you think it is, right? It's sort of no, that's not a path, right? How about that? Do you think that's a path? Yes. So it's not just a sequence of edges, it's a sequence of edges where subsequent edges share a vertex, right? V1 to V2, V2 to V3, and so on, right? So you can define it mathematically, but it's what you think it is. Okay? It's a sequence of edges, it's just a sequence of edges where the middle ones share an endpoint, right? Go edge to vertex, and so on. So what's the length of this path? For that path, okay, with this abstract path I have here? What's the length of that path? V1 through Vk? Yeah, it's k vertices or k minus 1 edges. So it depends on what you want to call the length, right? Does that make sense? There's k edges there, and there's only k minus 1 edges, but there's k vertices, right? Okay. Now, a cycle is just a path with v1 equals vk. Now there's always this subtlety of definition of path. It's sort of the same definition as path, except vk is equal to v1. So what's the length of the cycle? Again, in this case, there's k minus 1 vertices and k minus 1 edges. So the number of edges and the number of vertices are the same, right, in a cycle. Okay, just you should be thinking of this, right, to keep you warmed up. So path is usually simple, no repeated vertex, and when we call a cycle, we usually mean it's simple. If you get confused, just ask us. Sometimes we're a little loose with this terminology. The notes, I think we've cleaned them all up, but don't worry too much. We don't ask tricky questions about that. That's not the point of this class. The point of the class is to reason at a more sophisticated level. Okay, so walk is a sequence of edges with possibly repeated vertex or edges, and a tour is a walk that starts and ends at the same node, so it could also have repeated vertices and edges. Okay, so these are the 4 things. But a cycle and a tour are related. Quick check. A path is to a walk as a cycle is to a... Right. I mean, the difference between a path and a walk is you're allowing repeated vertices. A cycle, a tour doesn't generally allow repeated vertices, and a tour does. Okay? Okay, so now there's also directed paths. Okay, and is that a directed path? Now that's a sequence of edges where every pair of edges does share an endpoint. Would you call that a path in this directed graph? No, obviously not. They're not directed in the right direction. So you want to use ordered pairs, and you can always generalize all these things, concepts to that. Okay? Okay. So these are all analogous. Okay, so now we're going to talk about connectivity. Again, these are things that, I'm just formally defining. Yeah. Yeah, don't worry about it. The tour has repeated vertices. They can have repeated vertices. Yeah. But again, don't worry too much. But yeah, a tour has repeated vertices, and a walk has repeated vertices, and a tour is like a cycle essentially with repeated vertices, with possibly repeated vertices. Like a cycle is a tour. Right. Okay. So U and V are connected if there's a path or walk between U and V. Okay? And you can generalize this to directed. I'm talking about undirected. A connected graph is a graph where all pairs of vertices are connected. Okay? What that means is for all U and V, there's a path between U and V. Or, okay? A path or a walk. Okay? If one vertex is connected to every other vertex, is the graph connected? Now remember, the definition is that all pairs of vertices have to be connected. Okay? Now I'm giving you a condition, and I'm saying one vertex is connected to every other vertex. It's an undirected graph. Now, is it true that the whole graph is connected? All pairs have to be connected, not just one person to everybody else, right? Yes? No? So it is. It's true. Yes is the answer. So for any UV, you could obviously go from U to X and then from X to V. And it's a U to V walk. And I used walk here. I threw in the walk in the definition because, a walk, it may not be simple, right? Because the path from U to X and from X to V may use the same edges, right? X may be off to the side. Okay? So that would be a walk and not a path. But you could modify the definition to walk or path. It doesn't matter. You can make the path simple if you want. You can think about that. Okay? Because essentially, if you repeat a vertex in a walk, right, that means you have a cycle there, or a tour at least, right? Because you started at a place and you came back and you just cut that out, and now that's just a shorter walk, right? If you come back to the same place, you could always make your walk shorter. Okay? Okay, there's nothing, this is all very intuitive. I'm just sort of setting it up formally. Okay. Is the graph above connected? This is not a hard question. Who do you think? Yes. Okay. How about now? Is it connected? Okay, so now there's something more interesting you can say about the graph. There's more definitions one needs to make. Okay? What are the connected components? Okay? So I'm claiming these are the connected components, okay? These are them. And the definition that I'm applying to get this, it's the max, each connected component here, so there's 3 of them, right? You see them, 1, 2, 9, and 6, and then that big one up there, okay? So each of those are connected. Every pair of vertices in each one of those components are connected by a path, okay? So it's like if you just took that set of vertices, you'd have a connected graph. Okay, and a connected component is the maximal set of connected vertices. Okay, so maximal. Okay, so this is, I'm adding this word maximal. It's a set of connected vertices, but it's maximal. So is 10, 7, and 5 a connected component? Well, all of 10, 7, and 5 are connected to each other. But is it the maximal set where 10, 7, and 5 are connected to each other? Is there another vertex that you can add to that to make the set bigger and where all the vertices are connected to each other? Yeah, obviously 8 would work, okay? And you can keep adding, okay? So it's not a connected component. So the connected components are maximal, okay? You have a graph with some set of edges, and a connected component is any subset of a maximal set of vertices where all the pairs are connected to each other, have a path between them. Okay, so now an Eulerian tour is a tour that visits each edge exactly once. Okay, now we finally set up all the framework and all the terminology. Even gave you a proof, like some nice structure of graphs, that the sum of the vertex degrees is equal to twice the number of edges. Now let's go to another. So now we're going to come back to the problem that we were trying to model on the very first slide. So an Eulerian tour is a tour that visits each edge exactly once. Okay, this is the problem that we modeled. Okay? Okay, so any undirected graph has an Eulerian tour if and only if all the vertices have even degree and is connected. In some sense, his argument said that there definitely wasn't an Eulerian tour in some sense if the vertex degree was odd. But, in some sense, this theorem is saying that's the only obstruction and connectivity. You have to be connected. Obviously, you can't, if the graph consists of disconnected components, there's no tour that can visit every edge because you can't get from one to the other, right? There's no path. Okay, so these are just the obvious conditions. You can't have an odd degree vertex and you can't be disconnected, and then, in fact, you have an Eulerian tour. It's very cool. Okay? It's like all the possible tours you could have out there. It's a little surprising that this actually works. Okay, so first of all, I'm going to prove only if there is an Eulerian tour, it must be connected and all the vertices have to have even degree. Okay? So I'm going to assume that it's Eulerian, which means there is a tour that visits every vertex, every edge exactly once. Okay. Or the Eulerian tour is connected, so the graph is connected. That itself proves if you want to get from any pair of vertices, you just use the Eulerian tour. It gives you a walk between any pair of vertices. So since the Eulerian tour includes all the vertices, it goes. You can go along the tour to get from any U to any V, or back along it. Okay. Now, the reason it must be even is the student's argument here is that if a tour enters and if it enters a vertex, it must leave, right? It's a cycle. Think of it as a cycle, right? Every tour, if you look at the point of the view of a vertex and look at its adjacent edges, at some point the tour comes, you go along the tour, it comes into the vertex. Well, once you come into vertex, you have to be able to go out of the vertex. Is that correct? Right? And then if you come in again, what must you have to be able to do? Go out again. Okay? So the tour uses all incident edges. Therefore, V has even degree. Okay, so let me draw a picture of that, just so you know it. It's a very simple argument, just like the sum of the degrees is 2 times E, but it's a very powerful argument. Right? It's very cool. So you come in, you come out, you come in, you come out. So they pair up. Since the edges, the enter and leaves, pair up, then except for the starting node. Let's say you started at a tour and you traversed it. Okay? Now, for the starting node, you left in the first place. It wasn't paired up. But you end up there. So since you end up there, the first edge that left and the last edge that came then can be paired up. Okay? So that's the argument. And what it says is, there's this song, Hotel California by the Eagles. You can check out, but you can never leave. Well, it's not true for Eulerian graphs. You can always leave. Okay. So, the Roach Motel? I thought it was the Hotel California. Oh yeah, there's the Roach Motel too, yeah. You can check in, but you can never check out. But no, this one, they're a little bit more dark. They say you can check out, but you can never leave. So they're all artistic about it. Okay, so sorry. This is the Hotel California, the not Hotel California argument. I may refer to it that way in the future, but maybe he'll refer to it as the Roach Motel argument. We have our disagreements, so that's fine. Okay, so even plus connected. So that was easy, right? That said, in some sense, yeah, obviously if it's odd degree, you already have an intuition that if you enter and leave, something has to be even, right? You can almost guess it. So that was just the formal argument. Okay, so now we're going to do a picture. So I'm going to do this proof twice. I'm going to do this proof during the example, which I'm going to lay out here, and I'm going to do a proof without an example on the next slide. Okay? It's the same proof. It's the same argument. It's complete in both places. Okay? But here you get to use an example to get a little more intuition. Okay, so you start from a walk from some vertex on unused edges. Are any of the edges used now? No, all the edges are unused. Okay, we're starting an algorithm here. So no edges used. So we start from 1 and we start walking. Okay, go to 10, and from 10 I choose to go to 8, and I go to 4, and I just keep going. I keep walking as long as I can until I come back to 1. Okay? And now I got back to 1. Is that a tour? It's a tour, but does an Eulerian tour? Does it visit every vertex, every edge? No. Okay, but it's something, right? It came back to 1. Now we remove it. Okay, we take this tour and we move it. Okay? Okay. So, so you remove this tour, and now you have a graph, you remove some edges. It was connected before. If you remove some edges, it might not be connected anymore. Right? Okay, so now you think about the connected components. It may still be connected, then there's one connected component. Otherwise, in this case, there's 4. Okay? So you think of all those connected components, G1 through G4 in this case, but it's written in generality there. And each is touched by this tour. Now let's look at this tour that we pulled out. There's these edges, there's these blue edges, and each is touched by this set of edges, this C, okay, which I'm calling this set of blue edges. Okay, it's a tour we pulled out. Okay, each one of the components must have an edge from C that's incident to it. Why? Because G was connected. Okay? So when you don't have the edges, you see this component here, the 10758, has no edges leaving it. Okay? There's no edges from that component to any other, there's no path from that component to any other component. Therefore, there's no edge between that component and any other component. But we knew in the original graph it was connected. So there was an edge from 10, 7, 5, and 8 to some other component, at least to one other component. And so it must be one of the edges we removed. Okay? So that says each component has at least one vertex in it that has an edge from C in it, or C must include at least one vertex in each component. Okay? So V sub I is the vertices in G sub I. Okay? Okay, let's just let VI be the first node in GI touched by C. So what is the first node in this component, in this upper right component that's touched by C? 10. Right? If you think of this C as starting at 1, it goes to 10. It also touches 8, but let's just call it V sub I, or V sub whatever, is 10 here. And the first vertex in this upper right component that's touched by C is 4. And the first one in the lower right component is 2. Okay? Okay, so V2 is 10, V3 is 4, and V4 is 2. Okay, because there's 4 components. Okay, so now we're going to recurse on G1 through GK. Okay, and we're going to start in G1, we'll start at 1. The tour of 1 is nothing. The tour of this component up here, G2, is this upper left-hand component. We start at 10, and we recurse. Okay, we just recurse this whole algorithm. We start at 10, we take a walk, we remove a cycle. Okay, so in here, those are what would happen recursively. Okay, and then what do? Okay, so now what we had is we had the original tour C, right? And we have all these little tours of all the little components. So we should put them together somehow. Okay, and recursively, what I can be rest assured, whatever this red thing is, in this case it's just a simple cycle, but whatever this red thing is in this upper left-hand corner, it's visited every edge in that component. Okay? So those red edges have covered all the edges in that component. In this case, it's simple. But, right? So every edge in this subcomponent in G1 has been used by an Eulerian tour. We could recursively say we build an Eulerian tour, and we started it at 10, and we ended it at 10. Okay? And so on. The blue edges cover all the edges in the upper right component, and the whatever that color is, it's kind of gross, but whatever color, right? Okay, covers all the edges. So that's what I mean recursive, right? Okay, now we splice them together, right? We can easily splice them together. What we do is we start with C, and we start going along C. Okay, we start at 1, we go along C to 10, and then when we see 10, what we do is we take the red tour, and we put it in. What happens when we're done with the red tour? Where do we end up? Back at 10. So then, since C went to 10, it can go from 10 to somewhere else. So then we continue along C, and then the first time we see 4, a new component, we splice in that tour, and then we go until we see the first edge in this first node in this lower right hand corner, which is 2, and we splice in that tour, and then we return. Okay, that's the algorithm. That's the example. Basically the proof. Okay. Okay, so let's let's just, just review the proof essentially. But there's a couple of details left out on the previous slide, but let's just go over it again. Take a walk from an arbitrary node V until you get back to V. I tend to use node and vertex as the same thing. Okay. The claim is you do get back to V. That's the one claim I left out. I didn't argue that. Why do you get back to V? There's an argument. He calls it the Roach Motel argument, and I call it the Hotel California argument. Okay? The question is you keep walking until there's no unused edges incident to the vertex you're at. Okay? Or you get back to V. Now, for every vertex in the middle, if you enter, you can leave. Right? For every vertex in the middle, from V, you started there, and then you go to some vertex in the middle. Is there an unused edge that allows you to leave? Yes, because you came in. That means you used one of the edges. You know its degree is even, so it must have at least two edges. Okay, maybe you come in again. Well, you entered and left, so that means you used two of its incident edges, and you came back, and that means if you enter again, you've used three. But you know the degree is even, so there must be at least four. Okay? Except for V. V, you use this one edge. There's this extra edge that you've used at the beginning, right? You started at V, you left, you used an edge to leave, and now you're sort of have an odd number left. So, but that's okay. If you get back to V, that's fine. You're happy. You could just stop there. Okay? You just walk using unused edges. You don't care which one. This is a great algorithm. You don't have to know anything. You don't know what you're doing at all. You're just like, oh, I haven't seen this road before. I'm going to take it. That's all you have to remember. Okay? Okay, so then you remove the cycle C from G. The resulting graph may be disconnected because you removed edges. It was connected in the beginning, but now it's no longer connected. These are the components. Let VI be the first vertex of C that is in GI. Why is there a VI in C? Okay, G was connected, right? So a vertex in GI must be incident to a removed edge in C. This is what we argued before. Okay. And so each vertex in each GI has even degree. That's the third claim. Because why do we need that? Because we're going to run the algorithm recursively on each connected component. Why does each connected component have even degree? We've removed edges. Originally, every node had even degree. Now we remove some edges in C, right? Now, if we removed edges in C, it may or may not. It has less. The degree might be less. It might. Why is it still even? Okay, and it's connected, right? Because it's connected because it's a connected component, right? Okay. Well, the tour C has to have even incidences to any edge, any vertex in V, because if you entered, you left, right, for the middle vertices. And for V, when you left using one edge, and you came using one edge, so that's two, so you subtract those two edges. So that also keeps the degree for V being even. Okay? Okay, so now you find a tour Ti of GI, starting and ending at VI, right? That's just induction, right? Now we're using the same theorem. We have a connected component. Every vertex in that connected component has even degree. So we know there's a tour that visits every edge. Okay? And now we just put them all together. That's the algorithm part of your induction, right? You use the induction property. Here we're arguing properties everywhere, like as we go down into the induction to show we can validly apply the induction on the components. And then when we come out of the induction, we have to piece together all these pieces. We piece together the tour of each one of the connected components along with the C. And that's the action of the algorithm that you see when you go along C and you use V, you come back to VI, then you go to the next component, you use those edges, and then you continue along C. That is a tour. Visits every edge once. It visits the edges in C exactly once. And by induction, all the edges in GI are also seen. Okay? Good. Questions? Yeah.
So, I want to make sure that we're assuming there's a cycle already and taking the cycle out
well, we don't assume there's a cycle. We build the cycle. So we build this tour C, which let's just say for simplicity is a cycle, but it could be a tour. You could repeat vertices, okay? And then we take that out, right? But since it's a cycle, think about it as a cycle, okay? When we take it out for any node, any node in the cycle, how many edges have we taken out that are next to that node? 2, right? So now what we know is that every node that remains has degree 2, and that's why we're using inductively. Okay. Okay. Oh, it's I'm not going to give you a break. Okay. I'm going to give you some administration, but you can. Well, you don't have to pay attention, but I mean, just like the rest of the class. But okay. Okay. Where's my glasses? Okay. Well, so I have glasses. Okay. So there's this. You have to choose homework option or test option soon. Okay. So I'm going to give you some advice about that. Okay, or I'm not going to give you advice about that. I'm just going to tell you some data, okay? So the test option, you don't have to do homework, right? That's the point. You don't have to do it. You don't have to turn it in, okay? You don't have to do any homework henceforth. Okay, that's what the test option is. Yay, right? No homework, yay, okay. Okay, you should do the homework, okay? But whether you turn it in or not is on you. You are allowed to turn it in. You turn it in just like all the other students. We will grade it just like all the other students. At the end of the semester, we won't count it. Okay? It just won't matter. That's it. So, but you will get all the services in terms of our attention as the homework students. Okay? Okay. The homework option, you should do the homework. You don't have to do the homework. You could just lose the 15% if you want, but it's probably not a good idea. Okay? Okay, the truth. What's the truth? What should you do? The truth is in courses at Berkeley, in CS courses, your grade is a test, right? Eventually, that's how we assess you. The homework is some small part of the exam, and you're Berkeley students. If we give you homework, you basically all get 100%, right? You figure it out. You figure out how to get the points. Your parents, I taught my kids that. You got to get all the points. You just got to do that. That's what that's why you're at Berkeley. You know how to do that. So the variance is mostly in the exams, right? So whatever, and since these are really, that's how we're assessing you. We're assessing what you know based on the exams. Okay? Most homework students get near perfect scores on the homework. So this is always true. So it doesn't really matter, the homework, other than the behavioral aspects of doing the homework. Doing the homework, we strongly believe doing the homework will help you learn. In fact, we actually think the homework does more than help you do well on the test. It actually gives you a deeper experience. So I think doing the homework and working on the problems is a good idea. But, if you don't want to, I don't care, right? So, I also don't care, partially because I don't want you to, like sometimes when people do the homework, they just have to get the points, and they write something that, that kind of parses, but they don't understand it. And I don't know that that's an effective use of time. Okay, so how will you do? Now that's the question. What is I guess, okay, let's see if I can see how you will do. Click. Uh-oh. Okay, let's try it this way. Click. Oh, please. Okay, I could do it another way. Oh, my Firefox is not happy. Okay, well that's a problem. How do you live without a browser? Okay. Firefox? Yes. Okay. Okay, jobs, events. Okay, now let's see if it works. No. Okay.
No, Linux usually works. You're wrong about no Linux. Those other operating systems are a disaster. It's not even a joke. I don't know why you people use them. It's really problematic. Except I'm not giving a very good demonstration about how great Linux is doing, but no. The Firefox is just telling me no. Like reinstalling is always a dangerous idea. Okay, so I'll show you on Thursday. But there's a survey because you have Friday, so I guess I don't know what's going on. But here, let me see if I can get this to work. Okay, how will you do? I think it doesn't make that much difference. I think it's really up to you. The data is noisy. I did an analysis where I got everybody's grades in previous classes. On average, the homework group does a little better than the test only, but if you control for their grades in like 61A or Math 54, they do about the same, maybe a little less worse. And there's a survey there which I can show you, or you can look at. It's posted on Piazza. All this data is posted on Piazza. I've shared. I don't want to hide anything from you, right? That's not good. So it's posted on Piazza, and there's a survey of previous. And guess what? The people who do the test only spend a lot less time doing the homework because they don't do the homework. So that's what the survey says. And the survey also says everybody's happy with most of the people are happy with their options in retrospect, even after they get the grade. I did the survey at the end. Okay? So mostly people are comfortable with what they chose. There's a few people that are regretful. There's a few more people that are, on average, the test-only people are happier, but there's a few more people who are really say I shouldn't have done that. So you can see that, but I'll do that later. Okay. So now break time's over. I'm sorry, but you got to have a break while you watch me struggle with my computer. Sorry. Okay, graph that can be drawn in a plane without edge crossings. So this is a planar graph. It's a property of the graph. Okay. First of all, even before I show you what I'm talking about, I want to tell you this definition is kind of subtle. It's a property of the graph. You see, that can be drawn? That's sort of weird. Okay? So think about that when I show you the examples. Is that planar? Is that graph planar? Yeah, it can be drawn in the plane without edge crossings. It is drawn in the plane without edge crossings. Right? Yes, for the triangle. Okay. 4-node complete graph. Now, is that graph planar? Okay, so I warned you, and I'm glad I warned you, but do you see why it's planar? This is why it's planar. Okay, that's the same graph. Okay, there's two different drawings. One drawing is not drawn where the edges don't. One has an edge crossing, and one does not. Okay? A complete graph means every possible edge is present. Sometimes we also call them a clique. I think in high school you called them a clique, but I think mathematicians tend to call it a clique. But that's a complete means every edge, all the pairs of edges are there, right? That's what complete means. How about 5-node complete graph? Where is it? It's not there. Okay. It should have appeared. Okay, so my animation is not working. But the 5-node complete graph, what? Okay, let's just leave it because my computer is not behaving. So I'll tell you why it's not drawable later. But first of all, already you should think there's something deep going on here. Like I'm going to show you that the 5-node complete graph is not drawable in the plane. What does that mean? I have to tell you, no matter, like you saw this with the 4. When I went from this drawing to that drawing, I was like, oh, I can draw it this way. At first it's not clear, but then I said, okay, well, in fact, there's a way to draw this graph in the plane. Now, the natural drawing of the 5-node complete graph, there's crossings all over. Now the question is, now I have to prove to you that no matter how you draw it, you have to have a crossing. Okay, so that seemed hard because I have to argue against every possible drawing. Okay, so this is not an easy thing to say that the 5-node complete graph is not planar. It's not easy to see how to do that. Okay? Okay, and we'll go into that later as to why that's true. How about this graph? Is that drawable in the plane with no crossings? Two to three nodes. This is what I call a bipartite graph. There's two groups of vertices. There's the one on the top and the one on the bottom. And all the edges go between different types of vertices, the top and bottom. There's no edges between the vertices on the top or the edges on the bottom. That's why it's called bipartite, two parts, right? And they only have edges to the other part, okay? Yeah, that's the drawing of this graph. That's the same graph if you think about it a little bit. The vertices in the middle are connected to the vertices on the end. All the vertices in the middle are connected to both vertices on the other side. How about this one? Is that drawable in the plane without any crossings? Now, what I have to do to show that it is not drawable in the plane without any crossing, and somehow I have to prove that to you. I have to prove that no matter how you draw the thing, no matter how you move around the nodes and curve the edges or whatever you want to do, there's no way to draw it in the plane. Okay? So that's what I have to do to say no. Okay? So why is this true? I'm going to show you. Okay? Okay. Okay, so where is K5? Okay. So let's look at let's define another concept. Now we have graphs, which have vertices and edges. And now we're going to also have a drawing. Okay? So we have a graph and its drawing. Once we draw it, we can define another concept. And we could define this thing called faces. Okay? So the faces are the connected regions of the plane. Like, let's just look at this drawing of the triangle. Right? What are the connected regions of the plane? How many faces let's look at this triangle. How many faces are there? How many faces are there in the drawing of the triangle? So it's a graph and a drawing, and now in this drawing, what a face is a connected region of the plane. How many faces? Is it 2 or 1? It's 2, because there's the inside and the outside. So there's this thing that we sometimes call the infinite face. Okay? So that triangle is a simple cycle, and a simple cycle always connects, it has 2 pieces. It's called the Jordan curve theorem. We're not going to go into that, but just it's exactly what you believe, right? There's the inside and the outside. Okay? Okay. How many faces does this drawing have? Yeah, 1, 2, 3, 4. Okay? And finally, how many faces does this last drawing have? 3. Okay? Okay. So I just want to show you something, right? Like in this sense, for the triangle, how big is the face? How big is the face in terms of number of edges? So now when I talk about a face, I could talk about the connected region of the plane, but let me also think about the edges next to that face that form that face. So in the face inside, how many edges are in the boundary of that face? 3. Okay? And now for K4, all the faces have what, and how many edges in the boundaries? Well, there's 3 in this one, there's 3 in this one, there's 3 in this one, and there's 3 on the infinite one. Right? So you could also think of the face as the set of edges, or the cycle that forms it. Right? The face is the connected region of the plane, but combinatorially it's also the set of edges that forms that boundary. Okay? So in this case, what about this bipartite graph here? How big are the faces there? They're all the same size, but how big are they in terms of a number of edges? 4. Not 3. Right? Not 3, but 4. Okay? Because 4 is one bigger than 3. So 4 is not 3. Okay? Now, yeah, I know. I just think I'm hilarious, but nobody else knows what I'm talking about. So what I'm talking about is this is a bipartite graph. So faces are cycles. So I'm going to tell you something about a bipartite graph. Any cycle has to have even length. Okay? So there can't be any this is a bipartite graph that has 2 sides. if you want to come back to your same side to finish your cycle, you have to take an even number of steps. Okay? So in a bipartite graph, all the faces have even length, at least 4. Okay? So just something to play around with. I'm foreshadowing. Okay, so if V is a number of vertices, E is a number of edges, and F is a number of faces, now we can state this theorem, this formula. Okay, so that Euler's formula. It's a connected planar graph, has V plus F, where F is the number of faces, equaling E plus 2. Okay? Where does this come from? We'll prove it probably on Thursday. On Thursday, actually, that's the plan. But it's a simple formula, right? It says, okay, now we have something we can work with. If I want to prove something is planar, I just have to prove that it can't satisfy this formula, or not planar. I just have to, if I want to prove it's planar, that's kind of intuitively easy. You just need to give me a drawing. Okay? If on the other hand, I want to show that it's not planar, I have to show that it can't satisfy this formula. Okay? And in some sense, you can sort of see, if you have lots and lots of edges, in some sense, you sort of think, well, maybe that's a problem, but maybe you can make enough faces to deal with it, right? But in general, intuitively, the more edges you have, the harder it is to make a planar drawing. Right? Okay. So a triangle. Let's check the formula. So the triangle has how many vertices? It has 3 vertices. It has, for a triangle, V is equal to 3. The number of faces is 2. The number of edges is 3, and the number of 2 is 2. 2 is the number 2. So 3 plus 2 equals 3 plus 2. So the formula holds for the triangle. Okay, for this drawing, for this drawing, it's a property of the drawing. So it also holds here. There's 4 vertices and 4 faces and 6 edges, and you add 2. K2, 3, 5 plus 3 equals 6 plus 2. So it says for any drawing of a planar graph, the number of vertices plus the number of faces equals the number of edges plus 2. Okay? And now I've given you 3 examples, and once you get to 3, by induction, the formula is true. Right? No. Okay. Sorry. That was a joke too, but not. Okay. I think it's hilarious, but I don't know. Yeah. Okay, so there is, when you want to come up with theorems, it is true. You come up with some examples, and at some point you're like, okay, I kind of believe it, but I don't know. This one doesn't have enough structure to actually say anything. Okay. Greeks knew the formula for convex polygons. Okay? So they knew this formula. So now if you think of a convex polygon, a cube is a convex polygon. So if you think about it, what's the number of vertices here is 8. The number of faces is 6. The number of edges is 12. So 12 plus 2 equals 8 plus 6. Right? For a cube. Right? So that's for a convex polygon, the notion of a face is fairly straightforward. It's one of these flat things. Right? Okay. So now 6 faces in this cube. The number of edges is 12. The number of vertices is 8. It's a connected plane. Well, now I'm using some other theorem about some planar graphs. I don't know why I'm using a theorem about planar graphs about polyhedron, but I am. But it happens to hold. So if you take the same formula for polyhedron, it also holds. Okay. And that's because they knew about induction, they knew about the natural numbers, and now when you remove the vertices from the polyhedron, things sort of complicated happen, right? Like the number of faces that decrease is sort of weird or something. They just couldn't prove it. Okay? But in some sense, a convex polyhedron without holes is equal to a planar graph. So the way you can see this prove this theorem about polyhedron is you can actually just prove Euler's formula for planar graph. Now, why is that a planar graph? Okay, so I'm going to convert that thing on the left, this cube, into this planar graph on the right. Okay? And how do I convert it? Well, I take a point inside of this polyhedron, and I just blow it up. I map each point I just draw a line from that point in the middle to every point on this surface, and I map it to the surface of a sphere. Okay, a sphere is not a plane, but okay. Right, that's what I'm doing here. I'm taking that cube and exploding it to be mapped onto the surface of the sphere. Okay? Then I'm going to take the sphere, and I'm going to put a point on top of it and draw a line between every vertex from that north pole through this point, and that maps it into the plane. Okay? So I've mapped the polyhedron to the sphere, then I mapped the sphere into the plane. Now this point N, where does it map to? Where's this point? Where's the north pole mapped to in this mapping? Well, the north pole basically is infinite. It doesn't get mapped anywhere. It's just the infinite boundary. Okay? So other than the north pole, everything else is mapped to the plane, and this is the picture you get afterwards. And now you can see that each region, each face in this original thing corresponds to an area on the sphere, which is separated out by these lines, the edges where the edges are mapped. And now each face in this picture, when you do this, is mapped to a connected area of the plane in the same way, except for the face that contains the North Pole, which is now the infinite face. Okay, so this says that polyhedron, this formula for polyhedron is the same as the formula for planar graphs. Okay. So in some sense, there's this mappings that you can map the sphere to the plane, you can map polyhedron to the sphere. Okay, topologically. So they knew this formula for polyhedron, but Euler actually had to prove it much later, apparently. Okay, that's K5, by the way. Okay, so now I'm going to show you that these things, there's no way to draw them so that they can be mapped, so that they can be drawn in the plane. Okay? V plus F is equal to E plus 2 for a connected planar graph. That we know is a property, which I'll prove on Thursday. Nice proof, simple. We consider simple graphs where V is greater than or equal to 3. Okay, this any graph with fewer than 3 vertices is planar. Okay. So okay. So now, if V is greater than 3, let's look at these two drawings of these two graphs. Okay, so there's this triangle and there's this path of length 2. Okay. How many face edge adjacencies are there? Okay, so what I'm doing is I'm going to do almost the same argument I did at the very beginning of class about incidences. Incidences involve an edge and a vertex. Okay? So now I'm going to talk about something else. How many times does a face touch a edge? Okay? So in this case, this face touches these 3 edges in the triangle. Right? And this exterior face touches these 3 edges. Okay? So that's what I'm counting. I'm going to count those things in 2 ways. Okay? Okay, so now I'm saying there was from the point of view of the face, right? This face touches this edge. Okay? Now let's do it from the point of view of the edges. I'm going to say this edge touches this face. Right? Now, for edges, it's sort of easy to count the face edge vertices, right? Face edge incidences. How many face edge incidences are there? Each edge touches a face on each side. Right? In this case, this edge touches the same face twice. Okay? So in this drawing, there's a big face, the infinite face. There's not two faces. There's only one face. But this face has an edge incident on this side and an edge incident on this side. So it's 4. So the face touches 4 edges. Okay? So now in any cycle, if you have a cycle, any face is adjacent to at least 3 edges. Okay? As long as V is bigger than 3. Right? So if you have a planar drawing, you either have cycles or things like paths. Now, if you have a path, you have a face that touches both sides, but it also touches other edges because a face has to have more than 3, right? Unless there's only 2 vertices. Okay? So, how many of these face edge adjacencies are there from the point of view of faces? Each face has size at least 3, let's say, and therefore, the face edge adjacencies is at least 3 times the number of faces. Right? Now, faces could be long. It could be that the cycle could be length 10. You could have a cycle of length 10. And in that case, you'd have 10F edges, but 10F is greater than 3F. Okay? So now each edge is adjacent to at most 2 faces. Right? Or actually has 2 face edge adjacencies. I should say equals. I should define it as equals. It's adjacent to 2 faces. It's creating 2 face edge adjacencies. One on both sides. Okay? So you know that 3F, 2E is equal to the number of face edge adjacencies. And 3F is a lower bound on the number of face edge adjacencies. So 3F is less than or equal to 2E. Okay? For any planar drawing. Okay? So, or F is less than or equal to 2/3 times E. Right? What I'm doing is I have this Euler's formula, right? And I want to talk about these graphs. These graphs I'm sorry, I should have done that at the beginning. The graphs only have V and E. We can only say something about V and E with these because we don't have a drawing for F. So I want to eliminate this variable F somehow. I want to get rid of it. So I want to find a relationship between the variable F and the variable E. In this case, I'm doing the variable E. Okay? Okay, so now we have this inequality is that F is less than or equal to 2/3 E. So now we plug this into Euler. We say that 2/3 E is greater than F. So used to be F was here. Inequalities confuse me. So let me just do this slowly. So this is V plus F is equal to E plus 2. Okay. So now what I'm doing is I'm replacing F by something bigger. If I replace F by something bigger, then we know this whole expression is bigger than this expression. Just have to do it carefully. So E equals less than 3V minus 6. Now we said this, and this is our intuition. The more edges we have in our graph, if the number of these edges becomes very large, it's going to be harder and harder to draw it in the plane. Right? There won't be room. And this is what it says. It says, well, in fact, I can't have very many edges. Okay? Compared to the number of vertices. Okay? The more edges compared to the number of vertices, you just get a big mess. Like if the vertices increase, then you could maybe, that's something else. But okay. So now let's look at K5. Does it obey this formula? What do you think? I'm telling you, I'm proving that K5 is not planar. So, and I'm saying every planar graph has to obey this formula. So how am I going to prove it? I'm going to prove that K5 doesn't obey this formula. So therefore it's not planar. Right? So this is easy, right? That's the number of edges, 4 plus 3 plus 2 plus 1. The way I'm counting them is I'm starting at one vertex and counting all the incident edges. I'm going to the next vertex and I'm saying I'm not counting the previous edge that was already counted. That's what the 3 is, and so on. 10 edges. Okay, so what is that? 3 times 5 minus 6 is 9. 9 is not greater than 10. Right? So nice, right? Like, I think this is stunning. How do you prove that there is no drawing? You prove some property about what planar drawings look like, and then you can use that to argue that there's not very many edges, and now you know that for these dense graphs like K5, it's not planar. Okay? Okay, so now Euler's formula is okay, so now for K3. Now K3, let's try it for K3. Let's look at the number of edges. The number of edges is, I should have put that. Okay. What's the number of edges? It's 9, right? We can count the edges from the bottom. The reason I'm doing this counting is because later in this course we're going to do a lot of counting, and it's good to get some exercise up front. Okay, so now we're going to count all the edges from the point of view of the bottom vertices, so we don't double count them. And each of the bottom vertices is incident to 3 edges, so that's 9. Okay, so the vertices are 6. So now we're going to prove this is non-planar, right? So 9 is less than or equal to 3 times 6 minus 6. It is, right? That's 12. Okay? So it doesn't violate Euler's formula, right? It doesn't violate the inequality that we had on the previous slide, right? Okay, but I promised you I would prove it, but I haven't proven it yet, right? I have proven that K5 can't be drawn in the plane with no edge crossings, but I haven't proven for K33. Okay? Okay, so that proof doesn't work. So we have to do a different one. Okay? Okay, so one of the things that we use there is that we said that, like, look at every cycle. Any cycle has to have length at least 3. Okay? But remember when I said K23 had no, the faces were all of size 4 because it was bipartite? Now, any drawing of this, is every face, any face corresponds to the cycle. So what's the minimum length of a cycle in a bipartite graph? Can it be 3? Can it be odd? Can there be any odd length cycles? Let's think about that. Let's start at the top node here. Okay. Or even any top node, how do I get back to this vertex? Well, if I take 1 step, I go to the bottom. And if I take 2 steps, I can't go back because it's a simple graph, right? If it's a cycle, I want to use different edges. Okay? We don't count it as a cycle unless you use different edges. So you go down here, up, down, and back. What's the length of that? It's 4. Okay? Every cycle has to have even length because to get back here, I have to take 2 steps. Right? To get back to the top half of the one side of the graph, I have to take 2 steps. So it says every cycle is even length. So every cycle is of length 4. So every face is of length 4 in a bipartite graph. In any planar drawing, each face corresponds to a cycle. Okay? And that cycle has to have at least 4 edges. Okay. Okay. Because all cycles are of even length, bipartite or edges only go between the 2 groups in these bipartite graphs. Okay, so now we do the same thing. Now we say that instead of 2 times E, which is another way to count the face edge incidences, is greater than or equal to 4 times F. Okay, for any bipartite planar graph. Okay, now so now now we do the same thing. This tells us that F is at most 1/2 E, or E 1/2 E is greater than F. So I replace into Euler's formula, V plus F is equal to E plus 2. Now I'm replacing V plus something bigger than F, which should be bigger than E plus 2, which implies that E is less than or equal to 2V minus 4 for bipartite graphs, planar graphs, for any bipartite planar graph. And that doesn't hold. Okay? So I proved these things are not planar using Euler's formula. Okay? Are there questions? Any questions? Yeah. Yeah, no, I mean, these are, in general, you can do stronger proofs for different kinds of things. But in fact, there's a big theorem for planar graphs, is that all the planar graphs all the graphs that are not planar are, in some sense, they contain K33 or K5. So these are the only examples. I mean, there are other graphs, they contain it in a very strict sense. Okay, we had graphs, we did a bunch of stuff. I would say, let me just go over one of the arguments on each one of these things. The arguments I want you to remember, okay? There's connectivity. For graphs, in terms of the basics, you should understand that the sum of the degrees is equal to 2 times the number of edges. You should understand that proof. It's a very nice, simple proof that you can generalize. That is exactly the same proof I used at the end on the face edge, same idea I used on the face edge thing. Connectivity, the algorithm for what's the key idea for the Eulerian tour? If you can enter, you can leave. And then argue about connectivity. Okay? Planar graphs, there's this Euler's formula, which is very nice. And there you have to understand the difference between a drawing and a graph. So the planar graph says there is some drawing. Okay? And then the Euler's formula, we're going to do that next time. But now, once you have a property about planar graphs, and then you think about what drawings must have, right? Each face has to have size 3 or size 4. Then you can sort of manipulate these formulas to say, this graph does not satisfy that formula. Okay? So those are the arguments you saw today. Okay. See you.